Welcome back, guys. We're continuing with stall. Last video, remember telling you tip has increase in this incidence. So this one is wrong. It washout is basically decrease of incidence from root to tip. So the tip has lower incidence angle, so when if suppose the airflow is hitting the aerofoil, the tip stalls little later since the angle of incidence of the tip is lower. So the time taken to reach the angle of attack at the stall angle, basically the critical angle, is longer, so the tip stall doesn't take place and the root stall. So make this correction: tip has a lower incidence and this is called washout. Alright, so now we'll continue with the factors affecting stall. Okay, factors affecting stall. Okay, so factors that are affecting stall: aspect ratio, okay, so high aspect ratio leads to high stalling angle, and that's why we prefer high aspect ratio wings to a certain limit, obviously. Then all up weight, okay, weight of the aircraft. So with increase in weight, you have increase in stalling speed. Okay, so this is governed by the formula V2 equal to V1 by W2 by W1. So for example, if the aircraft is V2 is new stall speed, V1 at W2 weight, and V1 is old stall speed at W1 weight. Okay, so basically if you increase the weight, the stall speed will increase and you will tend to stall early. Alright, and the general idea is 2% increase in weight will lead you to 1% increase in stall speed. Alright, next one is load factor. So increasing load factor, your stall speed shall increase, and this is governed by V2 equal to V1 load factor. Okay, and load factor is live load by dead load. Now live load is basically your lift and this is your weight, all up weight. Alright, so these are the factors basically affecting stall. Now important point to note here is weight does not affect stalling angle. This is a key point to remember. Okay, and also density altitude. If you remember the lift formula, if you use that, density altitude does not affect the indicated stall speed. If these are the few points that you remember stall, that's good enough. Alright, so now we'll discuss stall recovery. Okay, so actually speaking, different aircraft have different stall recovery procedures, but generally stall recovery, the steps that are followed is, so first, angle of attack must be decreased. Simply, that's all, because you have a high pitch attitude, right? If you remember the signs of stall and which we discussed in the previous video, angle of attack is increased, so to recover from stall, angle of attack must be decreased to unstall the wing basically. and generally maximum power is applied to regain the lost height. Okay, and on smaller aircraft, small aircraft like Cessnas and all, rudder is used to avoid spin. Rudder as in to make it a coordinated flight, alright? So whichever the side the trapezium is going, keep the ball in the middle. Basic concept, keep the ball in the middle, or the trapezium and the Garmin should be aligned with the wings level indicator. Okay, and on large aircraft, aileron must be used. To avoid wing drop. This wing drop and spin we shall be discussing soon. So that what exactly spin and wing drop is we'll be discussing. Alright. Then now we'll discuss movement of CP. Remember I discussed it for the various wing forms. So movement of CP, symmetrical aerofoils, virtually no movement. Okay, second, largely CP moves forward when approaching stalling angle. Okay, now this is an important point. At critical angle, the CP is most forward. Okay, any further increase in angle of attack, CP moves rearward. So this is an important point. Okay, and approximately, generally, that is at -4 degree, CP is at the most rearward position. Alright, so this is the movement of CP. Now we shall discuss, we have done how to prevent tip stall. I've discussed you can use route in yeah, so you can use vortex generators, wing fences, saw teeth, and vortilons, washout procedure, stall strips, and all that. So those are the methods to induce. Okay, now what happens with CG? Okay, so CG discussions: forward CG, aft CG. So this will give you stalling speed will be high, less stalling speed, that is lower stalling speed. Okay, so you have a forward CG, your stalling speed will be high and you'll stall very quickly. And aft CG, you'll give less stalling speed. Okay, and at forward CG, aircraft resists to enter a spin. This is an important point as well. Enter spin easily. Enters spin easily at an aircraft with aft CG. Okay, and this will lead to less stability. This will lead to improved longitudinal stability. Alright. So, and if you exceed the aft limit, suppose the aft limit is exceeded, so the stall conditions are very drastically worsened and the stall recovery procedure becomes really tough. Okay, now we'll discuss what is different types of stall. Different types of stall. So the first foremost important type of stall is the secondary stall. Now that is dangerous as well. Secondary stall. As the name suggests, secondary stall is basically when suppose the aircraft has stalled once. Alright, so if stall recovery procedure has not been applied correctly, then it leads to secondary stall. So basically, if you're recovering from stall and you haven't given the time for the aircraft to accelerate or to climb a particular altitude, and immediately you have given correction and pulled the aircraft behind, then it will lead to secondary stall. Secondary stall is very dangerous because it can lead to a spin. Okay, secondary stall is the stall when this recovery procedure has not been applied correctly and the aircraft stalls again. That's the second time the aircraft stalls. Alright, so next is your next we'll discuss super stall or deep stall, that is called. Okay, I'll discuss it on the next page. So yeah, super stall or deep stall. Now what happens with the swept back wing? This stall is a swept back, generally a swept back wing phenomena. Now what happens with the swept back wing, if you remember in the previous video I discussed, the downwash increases and the plane pitches up further. So this aggravates the stall. Suppose this is your aircraft, right? Now the problem with super stall is your swept back wings, right? So swept back wings increase the downwash that suppose you have a tail plane, high tail plane. Okay, so when it increases the downwash, there is a pitch up moment. So the aircraft pitches up rapidly. Okay, and this is called the super stall or the deep stall. The problem with this is the high tail plane. Now when the aircraft is stalled, there's a lot of turbulence on the tail plane, right? And this makes it very tough to recover because the elevator has lost effectiveness. Okay, so generally what is applied is, to avoid this, is a stick pusher or the stick shaker. Shaker and pusher there's a little slight difference. Generally stick pusher is used. So what happens with the stick pusher is, when the aircraft is approaching such a stall, the deep stall, the super stall, the aircraft has motors in the control column that push the nose down to avoid reaching certain angle of attack that will lead to a deep stall. So stick pusher is one of the stall prevention devices. Okay, so this generally happens on a T type of an aircraft. Okay, there's another form of stall, that is cross control stall. This happens when excessive cross controls are used at low speeds. Example, right aileron and left rudder, or any of the combinations basically. So when excessive cross controls are used at low speeds, the cross control stall occurs. This can be is also an extended application of climbing and descending turns. So when suppose your aircraft is doing a climbing turn and your speed is low, at that time if you apply a lot of cross control, the left aileron or right rudder or whatever to maintain, if you're out of coordinated flight, this can lead to a cross control stall or a basic normal stall, which can again lead to a spin. Okay, so is that clear? So this was about different types of stall. Now we'll discuss spin. So spin is difference in lift on both wings. So spin is the difference in lift on both wings. Now this is a basic definition, but it has a large implication only when, for a spin to occur, aircraft has to stall. So now what happens is, when the aircraft is stalled, if one side your wing drops, if you have applied aileron or anything of that sort, if the wing drops, the spin from above will look something like this, okay, into a vertical axis, and will keep rotating the aircraft like this and descending rapidly. And this spin will happen when the wing drops on either side. Say one side, left side, the wing drops, the nose will tend into the spin and the spin will be initiated. So there's a differential lift and on both the wings, and the spin occurs. Now spin is a very dangerous phenomenon because it is tough to recover easily on larger aircraft. And there's, again, for the spin recovery procedure also, there are not certain procedures that are for different aircrafts. Is basically different procedure, but largely it is throttle idle, second aileron neutral, third opposite rudder. This is for smaller aircraft generally, and different aircraft have different spin recovery procedures, but this idle, throttle idle, aileron neutral and opposite rudder, this will stop the stall, stop the spin. When just out of spin, you have to neutral the controls, push the aileron to neutral and your rudder to neutral, and then recover height if you have lost. Obviously you will have lost height in spin. Recover the height and then add power. Okay, so first you add power and then recover the height. First, because it's throttle idle or thrust idle, right? So then you'll add power. If you remember stall, we'll add full power. In this you'll have to throttle idle to reduce the loss of lift. Okay, so last part of stall is stall warning systems. Okay, stall warning systems. Now why is stall warning systems important? For the simple matter of fact that you don't want the aircraft to stall, right? So stall warning systems, you don't want the aircraft to stall. So generally we have, like, say we have few stall warning systems that are flapper switch, angle of attack vane, angle of attack probe, stick shaker we have discussed already. Stick shaker or stick pusher is a similar concept, and that's about the stall warning. Now the important point of stall warning system is we don't want to know about stall at the last moment, right? So stall systems are generally designed that they give warning 5 knots or 5% of CAS stall speed earlier. So the warning will be sent out to you perhaps 5 knots actually earlier. Which of them is greater? Whichever of them is greater. So at a stall speed, suppose this aircraft is stalling at 140. Alright, so the aircraft will receive warning at 145 knots or 5% of the calibrated airspeed. Which of them is greater? So this will give you time to analyze your stalls, analyze your flight path and recover easily. So stall warning systems are designed that way. Now there's something called as a flapper switch. I'll discuss that. Flapper switch. Okay, so flapper switch is something like this. So when generally flapper switch is designed such that the stagnation point stays above the, I'll use a different sketch. So it's designed so that the stagnation point stays above the flapper switch. But if the angle of attack is increased, right, if the angle of attack is increased to a certain extent of the stalling angle, the stagnation point shall move forward, okay, I mean below the flapper switch. This will lead to the closing of the flapper switch, and it will give a warning. So it is set for a certain angle of attack. Since I told you each respective aerofoil has a constant stalling angle of attack, so the flapper switch is designed such that it always shows that angle of attack and the stagnation point is below it, and it gets a warning. So that is a flapper switch. Now there's something like angle of attack vane. So suppose this is the plane, okay. So angle of attack vane is something of this sort design, right, that is attached to the wing, to the fuselage here, okay. So what happens is when the aerofoil hits this angle of attack vane, at normal circumstances it will be same, but if the angle of attack is increased, the vane, it will move internally from this position, it will move say upwards. It's similar to the flapper switch. And now we've discussed almost all of the stall warning systems, and we have discussed span-wise flow, how to avoid it. We've discussed different types of stall. We've discussed spin. We've discussed stall speeds, load factors affecting stall, geometric twist, vortices, fences. So that largely summarizes the stall. Now I'll discuss a table so that it's easy for all of us to remember, okay. So summary basically. Alright, I think I'm losing my sketches. So summary for stall speed. So when is stall speed increased? When is it decreased? So this I am splitting into two, okay. Stall speed will increase with increase in weight, and it will decrease with decrease in weight. Stall speed will increase with decreasing flap angle. Stall speed will decrease with increasing flap angle. Stall speed will increase with forward CG with rearward CG. Stall speed decreases with rearward CG. Then stall speed will increase with increasing swept angle and this will be decreasing swept angle. Stall speed will increase with increasing load factor, decrease with decreasing load factor. Okay, stall speed will increase with will increase when you are giving turning or pulling out of a dive, or basically an abrupt maneuver. Okay, abrupt quick maneuver, it will increase. And stalling speed will decrease with deployment of slats, because this will re-energize the boundary layer. Alright, deployment of slats. And stalling speed will decrease with high aspect ratio. Okay, and there are few other points about stalling speed increasing. It will stalling speed will increase with increasing ice, heavy rain, and turbulence penetration. When you're penetrating turbulence, your stalling speed will increase. The last important point is, we don't generally give a lot of weight on it, but it's important. Stall speed will increase with undercarriage or the landing gear extension. Okay, so that is the reason undercarriage is deployed at the last possible final moment, maybe like 4 nautical 5 nautical miles to land. All right, so now we'll discuss regarding critical angle. Summary: critical angle, this is the stalling angle. Okay, increases, decreases. Just keep in mind, if you note these tables down, your stall chapter is largely done. So critical angle will increase with leading edge slats. Why? Because slats will give you, it will re-energize the boundary layer again. And critical angle will decrease with trailing edge flaps. Critical angle will increase with low aspect ratio, decrease with high aspect ratio. Okay, third one, critical angle will increase with a swept wing. There's always remember there's a difference between the stalling speed and stalling angle. All right, so and critical angle will decrease with high cambered aerofoil. Alright, and yeah, one more is here. We have a point as heavy rain. So you'll stall very fast at a very low critical angle, lower stalling angle when you have heavy downpour. Alright, and weight does not affect critical angle. Alright, so this is an important point to remember. Okay, so that's all I think about stall. Maybe one more point we can discuss about CL, coefficient of lift, that is maximum CLmax. What happens to CLmax? When does it increase? When does it decrease? So CLmax will increase for a high cambered aerofoil and high aspect ratio, straight wing. We'll have a lot of CLmax for a straight wing. When you have flaps and slats and trailing edge flaps, and CLmax will decrease with low camber aerofoil, low aspect ratio, swept wing, and ice, so CLmax will decrease with ice or rough leading edge, okay, and or heavy rain as well. So you might wonder, there are few contradictory points. Say high camber aerofoil will give you decrease in critical angle, but it will give you increase in, so it's basically a compromise that we have to choose. That of wing form, you have to choose a compromise. All right, so that's all about stall. So we are largely done with the transonic aerodynamics. So like it and share it if you like it. All right guys, see you soon. Bye bye.